Hello and welcome to this short introductory video series about machine learning. My name is Bojan, and the main goal of my work is to empower more people to take advantage of machine learning by making it more easy to use. In this video series, we try to cover the most important concepts and show how they fit together without going too much into details. If you're a beginner trying to make sense of the field of machine learning, we believe these videos could help you get started. Here's an outline of the topics we'll cover in this video series. Each topic is formulated as one particular question related to the field. In this video, we will focus on the second question. As a quick recap of the previous video, we went over the various fields related to artificial intelligence and how they fit together. We said that artificial intelligence is a field of computer science that tries to solve some cognitive problems which are natural for humans but have proven to be very difficult for computers. For decades, it was dominated by what we call classical AI. It was characterized by methods to explicitly define programs which should be able to solve our AI problems. However, this proved to show limited success, so people came to the idea of letting the computer learn to solve a problem on its own by using observations from real-world data. The success of this field sparked massive research directions. Among them were artificial neural networks, which showed their full potential only when new computing hardware allowed us to scale them up into many layers, forming structures which we call deep neural networks. Another important enabler was when we started to be able to obtain huge amounts of data needed to train these networks successfully. This subfield became so popular that it got a name for itself. It was called deep learning. Now let's head over to the second question of this series that tries to look at what are the kinds of problems which machine learning can effectively solve. The first type of problem, which is among the most common ones, is regression. As an example, let's say we are given some data about employee salary and we plot it against their years of experience. A regression problem might ask us to estimate the salary of an employee given their years of experience. So for example, given an employee with 15 years of experience, we want to know what their salary should be. In general, regression problems are about predicting a real valued output variable, given one or more input variables. The second kind of problem is also very popular. It's called classification, and in this case we're looking at binary classification. For example, let's say we have data that relates the size of a tumor with the categorization of whether it is malignant or not. So a classification problem here would be to determine whether a tumor is malignant if we are given its size. For example, if the size is 20 grams, we want to know if it is malignant or not. In general, classification problems are different from regression problems in the sense that their output variable is not a real number. Instead, for binary classification, the output is a yes or no answer. In general, a classification problem doesn't have to be binary. If we have more than two classes, then we are talking about multi-class classification. A very common example is image classification. Let's say we have a dataset with images, and each image can be associated with a class. For example, a bird, a horse, and so on. An example multi-class classification problem would ask to identify the most prominent object on a given image. For example, given an image of a deer in a forest, we want to have a program that would return deer as an answer. In general, multi-class classification problems are a kind of classification problem where we have three or more categorical values to choose from. An important property of categorical values that appear in both binary and multi-class classification is that we can assume there is no notion of distance or order among those categories. In other words, a cat is equally quote-unquote close to a frog as it is to a horse. This is opposite to regression, where, for example, a salary of $5,000 is closer to a salary of $6,000 than to a salary of $10,000. The problems we mentioned so far all fall into the problem category called supervised learning. We have here regression and classification as subtypes, which correspond to real valued or categorical output variables, respectively. Classification is further divided into binary and multi-class, depending on whether the output variable can have two or more categorical values. In general, supervised learning is about learning to predict some output variable based on observations found in our training data. Furthermore, these observations contain correct pairs of both input and output variables. This is where the word supervised comes from. Since the training data contains the correct output value for each input value, we can say that the given correct output value can supervise our program during training. Now we move away from supervised learning and examine some different types of problems which constitute a class of problems we call unsupervised learning. The first example is clustering. Let's look at a dataset where we're initially given a set of data points distributed along a 2D plane. Our job is to group them together into some given number of clusters. Let's say that number is 3. This grouping should be based on their distance so that points that are close together land in the same group or cluster. To make it more concrete, let's say that the 2 dimensions on this 2D plane represent a person's net worth and yearly income. Then, let's say we want to come up with some way to group them into 3 tax brackets. This could be seen as a clustering problem. In general, we are given one or more input variables about individual data points, and we need to find a way to assign each individual data point to a cluster based only on the values of the input variables. The catch here, and that is what differentiates unsupervised learning from supervised learning, is that there are no correct assignments that are known in advance. In supervised learning, for each data point in the training dataset, we know the correct answer. But in unsupervised learning, this answer is not known, so we have to come up with a sensible categorization on our own. If we had the answers beforehand, then this would simply be a classification problem. Another quite common example of unsupervised learning is anomaly detection. Let's say we have a time series dataset containing energy consumption by some household over time. Our job is to find any segment of time where the data exhibits some irregular behavior. Whenever we need to have a way to recognize a problem without being explicitly told if the problem occurred or not. The way this is usually solved is by constructing some sort of model that is able to capture the regularity in our data. In the graphic, this is represented by the thin dotted line. As we can see, it does its best to follow the solid line. However, if we encounter a point where the solid line goes far away from the expectation given by our model, we can say that that point constitutes an anomaly. In general, anomaly detection is a problem where we are given a dataset with one or more input variables, and we need to discover some pattern that this data follows. We use that pattern to judge new incoming data and decide if it fits the pattern or not. If it doesn't fit the pattern, then we say it is anomalous. Of course, the catch here, based on which we classify this problem as an unsupervised learning problem, is that there are no known anomalies beforehand. Again, if the anomalies were known beforehand, then this would simply be a classification problem and not an unsupervised learning problem. To wrap up, we have seen 2 types of unsupervised learning problems: clustering, which is about finding ways to group data points together, and anomaly detection, which is about finding patterns in the data that can be used to discover data points that breach that pattern. In general, we could say that unsupervised learning is about learning a pattern and at the same time learning a relation between individual data points and that pattern. In anomaly detection, it is probably clear what the pattern is, and the relation is either anomalous or not anomalous. In clustering, the cluster itself can be thought of as a pattern, and the relation is the membership of a data point to a given cluster. We can see it here visualized. We have the training data where we only have inputs, and we learn a pattern and a relation to that pattern. To go once more over the basic types of machine learning problems, we have supervised learning, with 2 prominent examples being regression with real valued outputs and classification with categorical outputs. We further divide classification into binary and multi-class depending on whether there are 2 or more possible output categories. In unsupervised learning, we have clustering, which is about discovering groups among data points, and anomaly detection, which is about finding a pattern and identifying data points that breach that pattern. A commonly referred to concept in supervised learning is the so-called supervision signal. That is the output label, which is always an integral part of our training data and is there to supervise the learning algorithm by teaching it what the correct answer is. In unsupervised learning, the supervision signal doesn't exist. Hence, there is usually no notion of a correct answer. Therefore, our algorithm must discover patterns by itself and produce answers based on its relationship to the data. We will also go over some other disciplines that are related to artificial intelligence, but do not nicely fit into the two categories of supervised and unsupervised learning. For some of these disciplines, there is even a dispute among experts on how they should be categorized. One such example is reinforcement learning. It has seen a lot of success in various areas such as robotics, gameplay, online trading platforms, and so on. It assumes the existence of an agent that can make actions in some environment, and consequently, the environment can send it some observations about various events, including a special type of event which we call a reward. It is usually the goal of the agent to learn to perform actions in such a way that maximizes the total amount of rewards it can obtain from the environment. A concrete example would be a vacuum cleaning robot. This robot can move around and turn its vacuum on and off. Those are its possible actions. It has cameras and other sensors to observe its position in the environment and to detect the presence of dust. And the reward would be the amount of dust collected in a fixed amount of time. The robot should then learn to perform its actions in such a way as to maximize the amount of dust it can collect. Good behavior of the agent is thus supposed to be reinforced with larger rewards, which is where the name comes from. As we mentioned, some people classify reinforcement learning among other two categories of problems, supervised and unsupervised learning. On the other hand, some people see reinforcement learning as a separate discipline of AI that, in its bag of tricks, among other things, has machine learning techniques. There are several other disciplines of AI which we will briefly mention here. They all seek to build programs that exhibit some cognitive abilities, but we differentiate them based on the type of data they focus on. They may or may not use machine learning techniques to solve their problems. The first one is natural language processing, or NLP, which focuses on text that contains written human language. An example application would be sentiment detection, which tries to determine if some given text is written in a positive or a negative tone. The second one is computer vision, which focuses on images obtained from visual sensors, such as cameras. An example would be detecting a face in an image. For example, in a video camera, so the camera can work to ensure the area of an image remains in focus. The third one we'll mention here is automatic speech processing, which works with audio recordings of human speech. The most common example here is speech recognition, which allows us to give voice commands to our devices. As mentioned, a lot of people would classify these techniques as subfields of AI that may or may not take advantage of machine learning techniques for some of their problems. That's all we have for this video. We hope it managed to clarify some basic concepts. Make sure to check out our next video where we try to explain some building blocks that will help us understand how machine learning actually works to solve the types of problems we mentioned in this video. Finally, feel free to check out our website and learn about our very own effort to make it easier to use machine learning for your specific problem. You'll find all the links in the description.